Hi everyone, and welcome back to our YouTube channel. In the previous lecture, we learned the definition of a determinant, and we see how we can compute the determinant of a given square matrix by using its definition. We also learned about how to find the permutations of n elements and also how we can determine the sign of a permutation. Well, in this lecture, I will continue with some key observations related to this definition. In other words, we will make very important observations by using the definition of determinants, and we will produce some properties related to determinants that would enable us to compute determinants in an easier way. Alright, let's start with the very first one. Okay, let's say we are given a square matrix, and as we all remember, to compute the determinant of a matrix, this matrix should be a square one. Okay, let's say our matrix is given 2, 0, 0, 3, 1, 0, 1, 2, 1. Okay. Now we are given a 3 by 3 matrix here. And since we are given a square matrix, right, we can compute the determinant. We know that with respect to its definition. Alright. Now, if you notice one thing, this is a special matrix, and we learned about this kind of matrices in our previous lectures when I was teaching you the matrix operations and different types of matrices. And this is called, if you draw the main diagonal here, the principal diagonal or whatever you call, you see above the main diagonal all the values are equal to 0, and this kind of matrix is called a lower triangular matrix, right? Why? Because for all I strictly greater than j, we have all the components of the matrix equal to 0. Okay, but one certain question probably comes to your mind. Why I have selected this matrix? And what is the reason behind this? Okay, let's understand what is the reason. And I will also come to a generalization after showing you how to compute the determinant of this kind of matrix. So we have actually beforehand, what we know is we have a lower triangular matrix here, right? Because all the values above the main diagonal are equal to 0, and this kind of matrix is called a lower lower triangular matrix. Okay, but if we had all the values equal to 0 below the main diagonal, then this is called an upper triangle, right? So I will come to that point as well. But we are given a 3 by 3 matrix. That means, well, our permutations, starting with the one which has a natural ordering, our permutations have 3 elements. Okay, starting with the one which has a natural ordering in the form of 1, 2, 3. Okay, this is the first one. And then how many different permutations should we have? Okay, since we have 3 elements, we have 3 factorial permutations, right? So we have 6 different elements. In other words, 6 different permutations. Okay, let's write the other ones. P2 is equal to, okay, let's keep the first position and just swap the last 2. So we have 1, 3, 2. And how about third one? Well, and actually you can write these permutations in any order. That doesn't matter, because we will somehow find both permutations along with their corresponding signs and along with their corresponding multiplications. So that doesn't matter on the table where you put them. Okay, but we need to find them accurately along with their signs and multiplications. Okay, if the first position is 2, and then just swap the other positions, and P4, let's say P4 is equal to 2, 3, 1. All right, let's continue. Okay, let's move it a little down. And how about P5? And P5, right, P5 is equal to, right, 3, 1, 2, and P6 is equal to 3, 2, 1. Okay. Now these are all the permutations that we can produce where we have 3 elements. Okay. Now the second thing is we find their signs. We find the row p values, right? So let's find their signs. Okay. All right, let's find their signs. This is P4, this is P5, and in the end we have P6. Okay. All right. All right. Now how about the signs? Well, the easiest way to find the sign is, okay guys, so look at the first one. How many operations we need to have P1? Well, zero interchange would be enough, right? Because we already have the natural ordering permutation. So since it is an even number, the sign is +1, okay, if you all remember. How about for the second permutation? In how many different interchange operations can I convert it into the first one? So I just look at how many positions are different, and as you notice here, 3 and 2 are in wrong places, so only one interchange would be enough, okay, to restore the P1. So 1 is an odd number, so the sign is -1. How about P3? So if you notice, only 2 and 1 are in the wrong places, right? Their positions. So one interchange between the first and second position would yield me the first one. So it's again -1 because one interchange and 1 is an odd number. But in the fourth and fifth one, you see that all the positions are different. Here you see 2, 3, 1, but it should have been 1, 2, 3, right? They are all in wrong positions, so 2 interchange would give me the first permutation, which is a natural ordering. So we have 2 interchange here, and we also have 2 interchange in P5. So since 2 is an even number, then we have +1 and +1 for the sign of these permutations. And for the last one, as you see, 2 is in its right place, so only 3 and 1 are in wrong places, so one interchange would be enough, so we have -1. Okay, we found the sign of each permutation. Okay, now let's get back to another important point. Let's find the multiplication values. So how would we do that? So if you remember, our definition works in this way. So we have A1, P1. So P1 is 1 here, so A1, 1. A2, P2, and P2 is 2. How would I understand that? I look at the first permutation. P1 is 1, P2 is 2, and P3 is 3. So I just read the elements from left hand side to the right hand side. And in the same order, I write them in the definition. So we have A11, A22, and A33. And in the first row, I have the multiplication of the main diagonal elements, right? So what we have on the main diagonal, 2, 1, and 1, right? I just put the values here. So what is the result? And the result is equal to 2. Cool. So result is equal to 2. Okay, let's extend this line a little bit. Well, let's make it look better. Okay. Yeah. All Alright, now let's continue with the other one. So we have A1, but this time, right, P1 is 1, so no problem. So A2, P2 is 3, right, 3. So A3, P3 is 2. Okay, I'll look at the entries in the matrix. Alright. Well, the good thing is, guys, if you notice, A2, 3 component of the matrix is equal to 0, right? So one of these values, when one of these values is equal to 0, then I don't need to find the other values, because multiplying any real number by a 0 value will give me a 0 again. So this is 0, so I don't need to even find the other values, right? And the multiplication is equal to 0 as well. So for the first row, if I multiply 2 by its sign, right? Don't forget to multiply it by its sign. So 2 times plus 1 is equal to 2. But for the second row, what we have? It is 0 times minus 1, which is again a 0, right? So no contribution. Okay. How about the third row? In other words, the third permutation, P3. So I just apply the definition, right? So we have A1, 2, because the P1 value is 2 here. P2 is 1, and P3 is 3, right? I just read these elements from left to right and put them in their place. So A21 times A33. So what do we have here? So if you notice, A12 component of the matrix is equal to 0, right? So it is again a 0. And 0 times minus 1, again a 0. So no contribution from here as well. Okay, let's proceed to the fourth permutation. What we have here, okay, A12 times A23 times A31. And again, A12 component is equal to 0 if you look at the matrix, if you look at the values in the matrix A. So we have 0 here as well. Okay, so 0 times 1 is 0. How about permutation 5? So we have A13, then A21, then A32, right? And the good news is, if you look at the A13 component, it is again a 0. And if we have at least 1 0 in the multiplication, then the result would be a 0. And we don't need to we don't need to be concerned about the result of multiplication, right? Because it is equal to 0. How about the last one? Put the formula here. We have A13, we have A22, and we have A31. And again, A13 component is equal to 0, and this is also 0. Okay. And multiplying the zeros by their signs wouldn't change the result, right? That's why I didn't even try to multiply them by their sign, because 0 times sign, again a 0, right? So the last step is I need to sum up all these values that I find. 2 plus 0, 0, 0, 0, and 0 is equal to 2. Alright then. Now what is the result? What kind of a conclusion I come to? Well, here's the thing. If you notice, since we have a lower triangular matrix where all the values above the main diagonal are equal to 0, in this table, besides the first row, all other rows have at least 1 0, right? Because all the other rows below the first permutation will have at least one component above the main diagonal. And since all of this main diagonal, all of the values above this main diagonal are equal to 0, we have at least 1 0 in each multiplication, which means we have all zeros in all other rows as a result of multiplication. And what is the result? So here's the thing. Here's the key observation that we make here with respect to this example. If we are given a lower triangular matrix, then what is the determinant? We don't need to compute any other elements or any other multiplications or permutations. What we need to do is we just need to multiply all the elements that lie only on the main diagonal. And in this case, we have 2, 1, and 1 on the main diagonal. So multiplying these elements would be sufficient for us to compute the determinant if we are given a lower triangular matrix. That's a very important and key observation that we should make. Okay, and also, what would have changed? What would have changed if we had an actually upper triangular matrix? In other words, if I had a matrix like this, so say 2, 1, 4, 3, 1, 0, 0, 0, say 2. Okay. Now, and this matrix, guys, is an actually upper triangular matrix, say C. So how would I understand? Either of the main diagonal, we are given a 3 by 3 matrix, so we have a square matrix, right? And if you notice, all the values below the main diagonal are equal to 0, which means that we have an upper triangular matrix. And the result or the conclusion we just come to in the above example works for this kind of matrices as well. So if we have an upper triangular matrix, then if you notice, besides the main diagonal entries, all other entries will have at least 1 0 in their multiplication formula, right? While computing the determinant using these multiplications, they will have at least 1 0. For instance, well, the formula wouldn't change if you notice, right? Say, let's use a different color. Okay. Now, if you notice, okay, let's look at here. Let's make it a little smaller to fit into the screen. All right. Now, let's use red. Okay. If you notice, guys, this time, which components are equal to 0? Since they are all below the main diagonals, we have A21 equal to A31 equal to, right? You see A31, right? And also A32 equal to 0. So, look at these definitions. What we have here. If you notice, we have A32 here, right? And this will yield a 0 if I want to compute the determinant of this upper triangular matrix C. And we have A21 here, right? So this is 0, and the multiplication would be 0. And again, if you notice, we have 31 here, so this is 0. And A32, this is 0 here. And A31, this is 0 here, right? So the conclusion is the same. Even if we have an upper triangular matrix, the determinant of C, as in this example, would be equal to what? Would be equal to the multiplication of the elements that lie on the main diagonal. And for the matrix C, we have 3 times 2 times 1, which is equal to 6. So we don't need to deal with finding the permutations or their signs or trying to multiply all other entries with respect to both permutations and the components in the matrix. What we need to do is just find the main diagonal entries and multiply them, and that's the result if we have an either upper triangular matrix or a lower triangular matrix. And if we have a diagonal matrix, the same conclusion is hold again, right? So diagonal is almost the same. If a matrix is a diagonal matrix, then it must be both an upper triangular matrix and a lower triangular matrix. In other words, only non-zero elements in a diagonal matrix would be the main diagonal elements. So this means, suppose we have a matrix like 1, 3, 4, okay, 5, okay, and we have something like 0, 0, 0, 0, 0, 0, and again 0, 0, 0, and here's the zeros. Okay, now look at this matrix D. So we have a 4 by 4 matrix actually, which is difficult to compute if we are asked to compute the determinant by using its definition. Well, but what makes it simpler is we know a property that is caused by the definition of the determinant, and if you notice, all the elements below the main diagonal are equal to 0, and at the same time all the elements above the main diagonal are also equal to 0, and only non-zero elements are the diagonal elements. So this is called a diagonal matrix, and this is both an upper triangular and a lower triangular matrix. So what is the determinant? Alright, what I need to do is just multiply the elements on the main diagonal, and that's it. 1 times, 3 times, 4 times, 5. And this is equal to 60, right? That's it. So our key observation here is that if we are given an upper triangular matrix or a lower triangular matrix or a diagonal matrix as shown in this example, then finding the determinant with respect to its definition is easy for us, because what we need to do is just multiply the elements that lie on the main diagonal, and that's the determinant. Okay. And that's a very important key observation. Okay, let's continue with another one. Now guys, here's another example. Well, actually, each example corresponds to a very important observation that we should be aware of. Okay, now, say matrix E is given like this, okay? So, 1, 2, 3, 0, 0, 0, and 3, 4, 9. And the question is the same, of course. We're trying to find the determinant of this matrix. Okay. Well, look at this matrix. What is special about this matrix? If you notice, guys, let's use another color. The second row includes only zeros. So we have a 0 row here, right? But we don't know how would this situation contribute to the value of determinant, right? In other words, what kind of an impact will it have on the value of determinant if we have a 0 row? Or maybe we could have had a 0 column as well, right? So we will come to that point as well in a moment. Okay, let's first try to understand the 0 row case. Okay, if we have a 0 row, okay, again, look at the definitions. Alright, so say the second row is a 0 row. What this means? And this means anything in the second row is equal to 0. So A21 is equal to A22 is equal to A23 is equal to 0. Now look at the definition. Regardless of what the values are, since again we have a 3 by 3 matrix, the permutations and the formula would be the same. So we will be multiplying the same entries, right? Unless the size changes. Okay, so if you look at the definition again, well, we have in each row, so for instance, A22, right? We have, if you notice here, I show it in red, we have A22, and A22 is 0, then the first row is equal to 0. And here in the second row, we have A23, right? So second row is equal to 0. And we have A21 in the third row, and again a 0. And we have A23 in the fourth row, so that means we have again a 0. And in the same manner, in the last two rows, again, we have, as you see, A21 in the fifth row, and again the 0, and A23 in the last row. So in each row, actually in each multiplication, we ended up with finding zeros. So summing up all the zeros, again a 0. In other words, if a row is a 0 row, then its components will occur at least in one position in each multiplication. So which means that we have at least one 0 in each multiplication, and the result of each multiplication equal to 0. And summing up all zeros will yield us again a 0. That means if we have a 0 row, then the determinant is what? And the determinant is, in this case, equal to 0. Okay, so this is an important property, very important property. So if we have a 0 row, then the determinant must be equal to 0. And in this case, the second row is a 0 row for the matrix C, and we don't need to compute the determinant, it's equal to 0. And what would have happened if we had a 0 column? Well, this is the same situation, guys. So say we have a matrix F, right? Say we have a matrix F. And say we have all zeros in the first column and non-zero values in all other entries, okay? Then what is the result? So what is the determinant? So if we are asked to find the determinant of matrix F, okay, if you notice that we have a 0 column, so the first column is a 0 column because all the entries are equal to 0 in the first column. Well, that means, guys, in terms of the components, we have actually A11 equal to A21 equal to A31 equal to 0. By the way, I could have chosen any other columns. So second column or the third column would have been a 0 column. That doesn't matter. The important key observation here is that regardless of which column or row I choose, if they are all equal to 0, their components would appear in all of the formulas here, in all of the multiplication at least one position. So in each multiplication here in the table, at least one value would be equal to 0, which makes all the multiplications equal to 0. And summing up all zeros, again a 0. So that means if we have a 0 column, the determinant is again equal to 0. And this is another key observation, guys, that we should be aware of. So in the case of given a lower triangular matrix, upper triangular, or a diagonal matrix, or a matrix which have a 0 row or a 0 column, actually are important observations that we should make. Okay, and I hope you enjoyed this video as well. In the next video, in our next lecture actually, I will show you another method to find or to compute the determinant of a given square matrix. And This method actually is directly related to elementary row operations that we are extremely familiar with. And until then, have fun guys and see you in the next lecture.